Good morning, everyone. Hello from an Airbnb in the middle of nowhere. I'm pre-recording this talk for you because, unlike for most of you, my internet is not the most reliable. So hopefully this will get to you before tomorrow. I'm missing Akim's talk to do this, so I'm sorry, Akim. I apologize in advance. I'm here to talk to you today about binary populations. This is something that is currently a very big topic. When I started 20 years ago, it wasn't. Nobody cared about binary stars, but apparently they're now very trendy. So hopefully this will get you involved. I should say, first of all, where I'm from. Most of you won't have heard of University of Surrey at all. It's a small university just southwest of London. I say small, it's actually the same size as where I was before in Cambridge, so it's which you will have heard of. Same number of students, but we're a very new group. We've got 5 or 6 faculty now, and we're doing our best to educate as many PhD students as possible. So if you're ever in the area, and I say here just south of Heathrow, just west of Gatwick, if you're ever flying through London, when things are open again, then maybe we can have you in and have a visit and give a talk. It'd be really great. And that applies to all the other lecturers as well, but I know it's a difficult time at the moment for me too. Okay, so today we're going to talk about binary star populations. I'm going to split that kind of into 2 parts. So let's have a look at the slides here. You've already learned a bit about single stars, and I'm sure you know a bit about single stars already. You look in the night sky, you see them there. But we'll talk a little bit about them as well, because of course what applies for single stars also applies for binaries. So you can't really split the 2. Binaries are more complicated, as we heard this morning, but they are certainly, you need to know everything you need from single stars to understand binaries, so it does get a bit more complicated. We'll then talk a bit about stellar populations, and particularly what I do, which is stellar population synthesis. This is where we attempt to construct models of populations, much like people do. For example, in Germany at the moment, there's an election going on. People try to model the population to see how they're going to vote. We do the same, but we do it for stars. And in many ways, stars are actually a bit simpler than people, but that's another question, I guess. But we'll address many of the issues of how we do this, what this means, and why we do this. And how we address problems such as the huge parameter space problem, which is one that I think we'll hit on a daily basis doing this topic. I'll talk quite a bit about stellar modeling for population synthesis. The reason for this is that stellar modeling for population synthesis is not quite the same as you would do it for just modeling single stars. They're very closely related, of course, but we have some special techniques to try to get around the fact that we need to have very large numbers of systems in our populations. I will introduce you to my code, which is the binary C code. The reason for that is, of course, that I support it. I give you software support, and I've made a page where you can download all of that. I've put a link on the Slack, so you can find it there. And we'll go through a lot of examples in the second class for how you can run some things with that and how you can make your own populations and explore, because there's no better way to learn than to explore. Now, I've set this up so that I can draw on here. I can do things like this, and I can draw smiley faces. So I'm going to annotate these slides as I go through, if I try to remember. When we come to the actual talk, I will be following it with you, so you can ask me questions in the Slack, and that's probably the best place to do it. So hopefully I can answer questions in real time, which would be really great. Okay. So what is a population? Well, let's think of where the word comes from. It's a word describing human beings, of course. So you might think, well, we take all of the human beings on Earth, and then we try to make some synthesis of them. So we try to model them. And that actually is very difficult to do, both for stars and people. So what is a population? It's a group of objects of something. And I think you should all be very familiar with that, but the reason I point this out at the beginning is it's not obvious to everyone what a population means in the context of stars, of course. So in the context of stars, well, there's some obvious things. You've got here galaxies. I think that's pretty obvious that that's a population of stars. 10 to the 11 stars. It's at 100 billion stars in the Milky Way, for example. But you can also have things like you've got up here on the top right, which is a cluster of stars. So that's also a population of sorts, because all of these stars were born at roughly the same time. And so they actually provide us with a very useful population, because of course if all your stars you're looking at are born at the same time, it makes it a lot simpler to model them and to understand them. You can also have populations of planets, which is something that's becoming more and more popular. I mean, obviously planets are observed now with Kepler and so on, and so we see many more planets than we had, say 10 years ago. So populations of planets and also how they interact with stars is something that's very important. I think we have a talk on that this week, so that would be good. And then what is the other half of this population synthesis word? Well, what is a synthesis? Well, really what you want to do is to make one star. Okay, that's a synthesizing a star. And I'm sure you've seen these equations here. So these are the stellar structure equations. And Akim's talks will go through those, and he's written wonderful textbooks on this, and I highly recommend learning from those. Absolutely fantastic. These are 4 coupled differential equations. There are obviously more, because these 4 equations are only for the structure. If you want the evolution as well, you have to put in things like the rate of change of chemicals, and it gets very complicated and also quite time consuming. You will use MESA this week to construct some of these models yourself. But what you can get out of this are properties such as the lifetimes, the masses, radii and luminosities, maybe colors, the chemistry in the star, what it's made of, what the ejecta are into space, this kind of thing. And these are all fantastic. This is what you need when you model these things, to compare to observations, which is what the whole goal of this is compare to observations to understand what's going on. So then what you want to do next to make a population of these is to make many of these stars. So if you were using a MESA, for example, you would run 10 stars or maybe 50 stars on your big cluster of machines. You'd solve all of these complex equations, and remember there's thousands of shells in these stars, potentially, and also they have some phases of evolution where it's very complicated. The main sequence is easy, relatively speaking, but other phases are less so. So yeah, that's quite time consuming. But eventually you get statistics from these stars, and you get distributions of things, which is very important. So by distribution, I mean something like a histogram or something like that. Maybe you'd bin it like that, and you get a histogram as a number of stars, I don't know, as a function of luminosity, for example, something like that. I think that's the kind of thing that you would want. You also get other things, distributions of radii, chemistries, orbital properties in binaries, these kind of things. There's so many different things we can observe. And depending on which survey you're looking at, of course, it will give you different statistics. Okay, so statistics are the thing we're all about, and of course this is we live in the perfect age to study statistics, because big data is now the thing, machine learning, all this stuff is coming in. It's becoming much more important, and these give us some tools which we didn't have 20, 30 years ago to study statistics. The computers are also faster. They're not quite these old-fashioned machines that you see here. They're much quicker these days. And, on my phone I can run things that 30 years ago I couldn't do on my desktop. So that's fantastic. So what do we use these for in astrophysics? Well, they are a method to understand the stars. Okay, so we go from observations of a stellar population, and especially with something like Gaia, you're talking billions of observations combined. And then what we do is we synthesize some models and we somehow compare the two. And that's the statistical part. And we'll talk about that a little bit. I mean, I'm mostly into the modeling, but we'll talk about statistics because it's vital. It's why we do what we do. Right? And then the idea is that what you can then do is to improve the model based on the comparison. Maybe make some new predictions. Okay? And this is the cycle that we are always in astrophysics. We're always cycling between new observations, so we improve the observations, we use those to go back, test our models are wrong, we come up with better, newer ideas, and then the models are improved. And we have to do it this way. We can't do it in the way that possibly some other sciences work. Because one thing we can't do, of course, is experiment on stars. So, and if you were a biologist, you'd probably get some live cells or something like that, and you would perform experiments on them. We can't do that. We can't say we'll put some stars in a cluster or we'll just create a binary. Not yet, anyway. I mean, it may come, but as of yet, it hasn't happened. So until we get there, then I think we'll still be working on modeling these things, at least in our lifetimes. So why are stars special? And we can't. I've already said we can't experiment on them, and we can model them. But the one thing that's useful about stars is most of them are isolated. Okay, and it's not that difficult to certain other branches of science. I mean, here I've got a picture down here of some molecules. They look like water molecules. I mean, they may well be in a liquid. Now, you can model those molecules as being mostly isolated from the other other molecules. They don't interact other than through very weak interactions compared to their internal bonds. And then you just add up the properties of all the water molecules and you get what you get. So what we do with stars generally is similar. Most of the stars that I model, for example, are isolated single or binary systems, but then you add up their properties to get what's called the field stars in the galaxy or other galaxies. There are always exceptions to this, and you have to be careful. I mean, you see from our picture of water here, if the molecules didn't interact, it wouldn't be a liquid, it would just be a gas. It clearly is a liquid. The same is true of stars, of course. Stars can interact, they can collide, they can merge. These kind of things do happen. And we'll talk a little bit about that here, but it's a whole lecture course in itself. So. Now, I should say before we go on, there are two types of population synthesis. These two words combined mean two different things in astronomy. You'll often hear about spectral population synthesis. And what this means is you take a load of stellar models and you compute some spectra for them. This is how you observe them, right? You observe all the chemistry, you've got the chemical lines that you can see in here. And by the whole point of computing all of them and then adding them up, so you can make say a galaxy of them, that's called spectral population synthesis. That's not what we're going to talk about today, although it's very closely related. We will talk about what's called otherwise evolutionary population synthesis. And what that involves is making populations of stars and computing any properties of them. It doesn't just have to be spectra. So it's a much more broad topic. I mean, you could compute spectra, but you can also compute their chemical abundances. You could also compute their radii, their luminosities, their masses, these kind of things. So similar ideas, but not quite the same in the literature. So I have to say the spectral people are generally quite lazy. They will just say population synthesis, and they don't care about differentiating their particular type of population synthesis. So you as the reader have to be careful, and you have to try to understand what's going on. So it's just a little word of warning. That's just the language that we use. It's a little out of date. Okay, so if we have an isolated single star, what are its key parameters? And you must have done a little bit about this in Akim's lectures. So the first one, of course, is the mass. By far the most important parameter will be the mass. That will determine which evolutionary phases the star goes through. For example, a one solar mass star like the Sun will have a red giant branch. It may not get past that. It may just blow off its envelope and become a white dwarf. A bit more massive, it'll have thermal pulses at the end of its life and form a big planetary nebula. Very beautiful. Make lots of carbon, perhaps. Maybe it does, maybe it doesn't. If you have a very massive star, 10 solar masses or above, it probably explodes as a supernova. So you have a core collapse type supernova. So you have these many different types of stellar channels, and they all depend only on the mass, essentially. But there's also the metallicity. That changes things. So if you don't know what the metallicity is, if you've forgotten, that's 1 minus the hydrogen abundance, which we always write as X, minus the helium abundance, which is Y. So there's everything that's not hydrogen or helium in the star. And that's definitely the second most important parameter. That affects not only the structure through changing things like the opacities in the stars, it also affects things like the stellar winds. And there's a talk on that this week as well, which I'm really looking forward to. And finally, something that's not as well explored and probably not as important for most stars, but certainly for very fast rotating stars, the rotation rate is key. And it becomes very important because if it's extremely fast, you'll actually have rotational mixing potentially inside the star, which can then mix the star and change its chemistry completely. And that will change its evolutionary pathways as well. Now, most stars don't rotate fast enough to do that, but they probably have a little bit of rotation, so they have a bit of mixing, which can affect the chemistry at the surface, for example. It may not change the structure too much, other than by making them slightly oblate, slightly egg-shaped. But that's fine. That's a small change. So these are the key parameters of a single isolated star. So as I said, Akim's lectures will go into some of this. There's whole courses on this. You can go out and find them. Now, there are uncertainties in stellar evolution, and I'm just going to mention a few of these. Again, the other lectures will talk about these. The reason I talk about these is because all the uncertainties in single stars apply also to binary stars. And if we want to get to binary stars, we have to understand these. And I mean, this is an incomplete list, so please do not take this as being a final list. There are other issues as well I haven't talked about. But things like how much mixing there is, so convection, how much convection there is in the star, whether there's overshooting or maybe a bit of undershooting, we don't know. And the rotational mixing, I already mentioned, so rotation can cause mixing, just like it does in our atmosphere, it also does in stars. There's other mixing, such as thermohaline mixing, when you have material with a high molecular weight sitting on top of material with a low molecular weight. They should mix. I mean, maybe slowly relative to convection, but still, they should mix. There's diffusion of elements in stars. We completely neglect that in most of our models, but it can be very important on long timescales or in white dwarfs, for example. So there's lots of other ways things can mix. Mass loss rates are also key, so there's huge uncertainty with mass loss rates, particularly in massive stars, but also for red giants. For example, we know that there's mass lost on the red giant branch in low mass stars. I keep reading papers saying we don't know when. Is it at the tip of the giant branch? Is it during the giant branch? We don't know. And that, of course, is important to look at the evolution of the star. Magnetic fields are something that is very poorly understood in stars. I'm not going to talk about that today, but maybe Fabio can explain a bit about that on Slack for you if you want more. And also the explosion mechanisms of stars are things that we don't understand that well in some cases. Things like type 2 supernovae, I think we understand okay. Still not a convincing explosion. There's a couple of reasonably convincing explosion models came out recently, but it's still something that's in cutting edge. No one really knows how it's done. But at least we've got ideas for type 2s and type 1bcs. These are in massive stars that have blown off their envelopes, the 1bcs. The 1As, though, are a huge problem. They're a problem for binary models because these are thought to be accreting white dwarfs. So by accretion, I mean mass comes from a companion and sits on the white dwarf and then burns and eventually makes the core massive enough that it ignites, or maybe hot enough that it ignites. How to make enough of these and which systems they are is very difficult. Very difficult indeed. It's a big open problem. Despite these being used in cosmology, it's a huge open problem. And there's other things like gamma ray bursts, which are extremely important. I mean, these objects that have been seen around the universe, I mean, all the way back to high redshift 7, 8, stuff like that. They're very, very old objects. And where these come from is also a big uncertainty. So we have ideas, but I don't think any of them are fixed in stone. There may be main channels and other channels in all of these cases. So it's quite complicated. So this Hertzsprung-Russell diagram here, this is deliberately blurry because none of these tracks are fixed. You'll see them, you'll make them with MESA, but if you change the convection a little bit within the error bars, you will see that you get a different result. But what do we do usually in binary star physics to make our first synthetic population? And this is what you'll do with some of the examples that I've set. We do make some simplifications just to make it easier, just to keep the computing time down so that we can do things in a time that is short enough that we can do it for a class like this. First, the simplest thing to do is to fix the metallicity. And what that means is that your internal physics of the star, for example, it's then fixed by that, and we fix all the other physics as well. Presumably we choose our best parameters, whatever that means, however they've been calibrated. Normally we neglect rotation, at least most of the time we neglect rotation in the sense that we neglect rotational mixing and deformation of the star. In most of the models we still treat the star as spherical, which is not a bad approximation in most cases. And neglecting the rotational mixing is generally okay unless the star is massive, in which case it might not be okay. So we can also simplify the population itself by having what's called a starburst. Now, if you've never heard the phrase starburst before, this means that all the stars are born at time t equals 0 and none after. Okay? So if you look at the rate, the star formation rate is a function of time. At 0, you have a spike up to here, and then none after that. Now, why do we do that? Well, because that's, first of all, it's very simple. You can construct populations like this, and then you can apply a star formation rate later. It's very easy to then take this and convolve it with a star formation rate. So it's a convolution problem. It's kind of like a Green's function for the population. So that makes it very simple numerically and computationally. You can always apply a star formation rate later. And we are left then with one parameter of our list of complex parameters that we don't understand, which is the initial mass. And we can vary the initial mass. That's our first synthetic population. Now, the initial mass has a range. The lowest mass stars are around 0.1 solar masses. Should be solar masses. See, I can't even draw this morning. There we go. And the highest mass stars are around 100 solar masses, maybe 200, something like that. Doesn't really matter. And what we want to do is to sample the parameter space where our parameter is the mass. So we put some stellar models into the parameter space. Simplest way to do it, I've divided it up into 10, what are we going to call these? Boxes. Call them boxes for now. Put them into 10 boxes. You have different masses in each box. So for example, here I've got 5 in the first, 15 in the second, and so on. And you might think, well, that's a reasonable way to sample stars from 0.1 to 100 solar masses. I mean, stars less than 0.1 solar masses are essentially planets, so they're big planets, so they don't really burn hydrogen. And stars greater than 100 solar masses, well, we don't see many of those, so let's pretend they don't exist for this. And okay, so we're now between 5 and 95, and you might think, well, that's a great way to sample. But then what you want to do is to link this to observations. And what's the first thing you can see from observations when you look at stars? Well, it's their luminosity, of course. And especially in the Gaia age, we know distances to stars, so getting the luminosities is very simple for at least nearby stars now. Certainly, it's not so difficult. So let's say we want to compare our models, so we need a model for the luminosity as a function of mass. Now on the zero-age main sequence, that's right when the star is born. And this is roughly the same across the main sequence. You probably remember the Hertzsprung-Russell diagrams from Akim's lecture. The stars don't change much in luminosity on the main sequence. A little bit, but not a huge amount. So we can have a model like this one, where the luminosity is proportional to, say, mass cubed, roughly. It's a rough model, very simple. And I can then map from my mass straight to the luminosity. I've mapped here to log luminosity because it changes by many orders of magnitude. Always better to use logs when you have many orders of magnitude change. And you see what happens here. The 5 solar mass star has a log luminosity of 2.3. It's a bit over, a couple of hundred solar masses, a couple of hundred solar luminosities, for example, and so on. And you see, as the mass goes up, the luminosity also goes up. Exactly what you'd expect. And then you can compute statistics based on this, right? So what I've done is I've very simply taken my model and I've computed the mean and the standard deviation. The simplest statistics that you learn in high school, right? Hopefully. So the mean of this distribution is 4.92. So your luminosity of your stars is around 10 to the 5, 4.92 is roughly 5 solar luminosities. Now let me ask you, do you think this is a very good model of the stars that you see in the sky? And if you look up in the sky, you see a few local stars. How many of them are around 10 to the 5 solar luminosities? Well, the sun's not. That's 1 solar luminosity, right? None of its neighbors are. The nearest star, Proxima, is very, very dim. It's not very, very bright. And so on. There are a few bright stars out there, don't get me wrong, there are a few. But this is a very poor model for the statistics that we see in main sequence stars in the sky. And we can plot our distribution of luminosities, and it looks something like this. I've had to bin the data. It's very crude, of course. We only have 10 data points, so I've got a very crude distribution. But this suggests that most stars should be 10 to the 5 solar luminosities, and they're not. So it's not a good model, and we're missing something. So what we're missing are initial distributions for these stars. And by initial distributions, I mean, what is the probability that a star is formed? Okay, so this is where statistics starts really coming into our models, our populations here. Now, the probability depends on the mass. We know this because people have made many observations of stellar populations in the sky. And what they do is they observe the luminosities and they use a model to convert that to the mass. And then from the mass, you can calculate, what's this function, psi, which is the number of stars per unit mass. It's a probability density function. You can normalize that appropriately with a 1 over n there. And then it integrates to 1, as you would expect from for such a function. And so in single stars, what you do is you start with your probability density function here, which is this here, and that's very simple. In binaries, of course, it's a bit more complicated, and we'll come back to this later to some extent. In binaries, it's not just a function of mass. In binary stars, of course, you have 2 masses, right? The binary has 1 star and another star, but then you also have the separation between them, which can vary as well. So it's actually a multi-dimensional parameter space, but anyway. But this function depends only on the position in the parameter space. It doesn't depend on the age or stellar evolution or any other properties. It's only a function of the initial position. Remember, it's initial distributions we're talking about here. And this function here is called the initial mass function. You'll see this often. And if you haven't heard of it, it's something that you really should know about. And so, okay, so this is our initial mass function. I've designed it so you integrate it to 1. What does the function look like when we go from the observed luminosities to masses? This is something that, for example, Salpeter did many, many years ago. Other people have done that. You've probably heard of the Kruper or Kruper-Taut-Gilmore distribution. Chabrier does lots of these as well. There's many in the literature. If you do a Google search, you'll find 100 papers on this. So stars are just simply not created in equal numbers. You have different numbers of them. The probability of formation depends on the mass. And this is the distribution that you end up with. And what you see here is most stars are low mass. And indeed, if you look at the sun, which I can draw here, so we go up from the sun, we get to here, we're way outside the mean of the distribution. The mean is somewhere up here. So the sun is actually something, sort of 2 sigma outlier in the distribution, you know. So it's quite a difficult thing to put in. So these massive stars here, which we were talking about before, which are exciting because they make core collapse supernovae, things like that, they are really, really outliers. They lie way outside the distribution. So let's now apply a simple mass function, which is the Salpeter mass function. That's a typical function of mass, which is m to the minus 2.5. So you see it's a very, very quick drop-off with the mass. And let's apply that to our luminosities, or to our masses here. And what do we get? Well, we get that the low mass stars are far more likely than the high mass stars. Because 0.87 is much, much more than 1,000th. And so we need this weighting function to compute our luminosity function. So we have to multiply these probabilities, multiplied by the luminosity that we get. It's a simple calculation to do. And we end up with these numbers instead. And you see that contribution up here at the high luminosity or high mass end is very small now. We now get an average log luminosity that's nearer to 0, so it's nearer to 1 solar luminosity. This is probably 2 or 3 or something like that. So this is much more like what we see in the real sky without telescopes, or if you go out on a clear night and you go and look at the stars, this is much closer. And this is what the distribution we end up with looks like. Again, it's quite crude because I've only got 10 stars here, but that's fine. That's okay. It's probably not that different to what you'd see if you go and look out in the sky. So you need this initial mass function in here, or in binaries we need the functions of secondary mass and separation and things like that as well. Very important. So this is to give you an idea of the basic things we need to construct populations. Now there's also a time dependence in populations. We've only so far talked about zero-age main sequence models, but of course real models have time dependence. And you'll know from doing the MESA examples that stars are evolved in time steps on a computer. Time is not a continuum in a computer, it's split into finite chunks because time, you need to compute the model in a finite time, and if you have time steps that are too small, of course, it will take forever. So you split things, for example, the main sequence. You can see here we've split the main sequence into models with 20 or 30 time steps on the main sequence. If you want a bit more accuracy, you can have 100 or 200 or something. But of course, it all depends on exactly what you're looking at. So when you see this symbol in what we're going to discuss now, what I mean is the time step. That's the time between two models. And you can see here, for example, the Hertzsprung gap. There's only a few time steps in there. It's because the star flies through there at high speed. That's why there aren't many stars observed there. So it kind of fits. And then we then want to count from our models how many stars are in any given evolutionary phase. And the first thing we need to do is to work out how long they spend in a phase, because obviously if they spend longer in your phase of interest, there'll be more of them. Makes sense, right? So we count this time, which is I'll call big delta t. And from the models, each time step we can say, is the star in our phase or not? And that's what this function delta bar is for here. And so during the phase, I give that a value 1, and when it's not in the phase, 0. Very simple. Then I sum up over all time, so that's from tmin to tmax. I sum up over all of the time steps what this delta t, this time step multiplied by this delta bar function. All of the stellar evolution is in this delta bar. And that's why you compute these models. It seems very simple, but it's a huge amount of computation just to get to the delta bar, whether you're in the phase or not. So for example, if you chose a red giant phase, then delta bar would be 1 during the red giant phase. But you need to know that it's a red giant. It's difficult. The other thing that we have to put into the models is star formation. Okay, now the star formation rate is a function of time. We usually call that S of t, which is very simple, S for star formation rate. You can also see it called something like that, star formation rate. Sometimes they give it a symbol, it depends on the paper. But the relative star formation rate here, this is from Chiappini's paper in '97. There are similar ones out there, and these days, I'll show you some plots in a minute, different galaxies where we can model this. But the star formation rate varies a little bit as a function of time, and this is for the solar neighborhood, and it's the error bars on this are still reasonably large. Even with Gaia, the stellar star formation rate locally is not well known. But the units of this will be something like n sun per year into stars. So you will have so many solar masses of gas that's out there will form stars per year. Typically that's around 1 or 2 for the solar neighborhood. And you could do it for other galaxies. I mean, this is from Dolphin in 2005, but I mean, there are other papers that are newer. I just like this because of the colors. I like the way it's presented. You can see that these are in different galaxies. And you see the star formation rate differs in galaxies. And of course, this is where stellar population studies link to, for example, cosmological studies or galaxy formation. Because if you're studying galaxy formation, if you have two galaxies merge, you may trigger a load of star formation. So, and then you make a load of stars, which you'll see later. So it's a detective work going all the way back, but we need to put this into our population models to understand what's really going on. So there's time-dependent star formation as well. There's also cosmic star formation. Let's integrate this over the entire universe. Okay, and depending on how you observe it, there's infrared or UV observations, and I suggest reading this review here for more details. You can compute the log of star formation rate, and in this case, it's m sun per year per cubic megaparsec. So that's really over the grandest of scales that you can observe. This is an average. But if you want to say, for example, compute things like black hole, can't even draw, black hole, neutron star mergers, or possibly type 1As as well, if you want to look at the rate of type 1As, you're looking at the universe when you observe these. And so you need to use the universal star formation rate, which is this cosmic star formation rate. So for these kind of things, this is very, very important. And what you'll see typically is that at a redshift of 2 or 3, there's a peak in the star formation rate. And the peak in the star formation rate is because, essentially, I guess it's because the galaxies are running out of gas that's available to make stars. And then the rate drops as you get to the present time. Now, we've only really talked about single stars in this. Many stars are also binaries. Keep this in mind. We'll talk a bit about that later. We've discussed a little bit how they now have many parameters, not just one. They've got the secondary mass, they've got the orbital period or separation. These are linked. We'll see later that these are linked. Or the eccentricity of the orbit as well, because orbits are not perfectly circular between stars. I mean, Earth around the sun is not perfectly circular. Even the moon around the Earth is not perfectly circular. So. And also, bear in mind, and we'll come back to this a little bit later, there are many other model uncertainties when we talk about binaries. For example, mass transferring between them. We saw in the introductory talk this morning a little bit about common envelope evolution. That's a big mess that people in Heidelberg especially are working on. But there's other things, merging of stars, and Fabian works on that, rejuvenation of stars, the tides in stars are very important, angular momentum loss, all kinds of things. So there's a lot of other complications which come in, but these are on top of the single star uncertainties. Okay, so it makes it really difficult to keep all of these in mind when you're working on these kind of subjects. So now one of the complications with binaries, because we've got these initial parameters, it's not a one-dimensional space anymore. We can't just vary the mass. Even in the most simple cases, we can't just vary one mass. We have to consider two masses. So we've got the initial mass of what's called the primary star. So that's star 1. We've got the initial mass of the secondary star, that's star 2. And the initial orbit. Now usually that's just the period that we care about, the orbital period. I mean, like the Earth goes around the sun once a year. Similar kind of orbits for stars, typically. That's a typical orbit for a star around another star. We could also look at the separation. Kepler's laws link the two, as we'll discuss later. But it's a 3D parameter space. And that gives us some issues, practical issues, when it comes to computing populations of these stars. And something that I think is overlooked quite often by people who work on only single stars is how long it takes to make a population of binaries. Let's say you want 10 stars, like we had in our demo population that we did earlier with the luminosity distribution. Let's say n is 10, right? Then, okay, that's pretty simple. If you want to run 10 stars in Mesa, for example, let's say each of them takes roughly an hour to run. If you go from the main sequence up to the thermal pulses, maybe you don't care too much about the thermal pulses, and so you can stop it there. It'll take about an hour to do that. Then the whole grid will take about 10 hours with n equals 10. I mean, 10, remember, is not a great resolution, but it's enough to do some work, so you can go with that. But then what if you do the same for binaries? Well, in this case, you have a three-dimensional grid, okay? N times n times n. And you've got this factor 2 as well, because you've got 2 stars. And so you've got minimum 2n cubed hours, which is now 2,000 hours of CPU time. Now I can imagine if I'd set my undergraduates an exercise to run 2,000 hours worth of computations, it would never have happened. None of them would have succeeded. They would all have failed their course. I actually set them a few hours on Mesa, but it was not 2,000. You also have the issue with this that you've got to then save all the data, you've got to make sure this is sort of accountancy, sort of management of all of these systems, and that actually becomes quite complicated. Okay. The other problem is when you're working in binary systems, many of them don't do what it is you're interested in. So if you're looking at, say, black hole mergers, then that's all well and good. It's nice, but you can't just say, well, I'll start with a 20 solar mass and a 20 solar mass star and they're going to merge. You don't know in advance. So some channels are actually very rare, particularly those that have stochastic parts in the sort of random kicks in supernovae are a perfect example. You know that these systems will be very rare because most systems, when they have those supernovae, will just fly apart. They won't stay together. And so you're going to need, for these rare channels, you're going to need numbers which are maybe 100, not 10. And you can imagine then the numbers get pretty crazy. Right? You're going to run 1 million stars, maybe 5 million, maybe 10 million. And so your laptop will literally be, I had a colleague whose laptop was on fire recently. It's how it works. So the reason I bring this up now is just to keep this in mind as to why it is that we use slightly different techniques for modeling populations to modeling detailed models of stars. Okay, now let's assume we can make these populations. How do we count them? How do we count the numbers of stars? That's the most basic thing you can do. You can always then make other statistics, but you always need to count numbers of stars. Well, it's relatively straightforward. You have a star formation rate. This is how when your stars are born. You've got an initial distribution, which is your IMF, for example, your initial mass function. And you've got the time spent in those phases. That's the contribution in the phase while it's in the phase of interest. So what we do is we multiply those. We've got one here, and one here. And then here we have the 0 or 1 factor as to whether the star is a red giant, say, if you want to count red giants. You then have this sum. You have to sum between when the star is born, that's T min, to some maximum, T max, which could be the age of the universe. That's the longest possible time you need. And then you have to sample over all of the stars. This I is just a generic counter, which says count through all the stars that are born in your population. And I, of course, could go up to 1 million in some cases. In real systems like the galaxy, it's 100 billion. So it's a big sum, and this double sum becomes very expensive. I don't know how much money you've got, how much CPU time. We were talking at the beginning about saving CO2. Not running huge numbers of models of stars also saves CO2. So you've got to think carefully about which ones you run because these numbers are huge. Now, if you have a population of binaries, it's slightly more complicated again. The reason is these are the same, these factors here. This one is different. I've now got an initial distribution, which is a function of 3 parameters, the 2 masses and the separation, or possibly the period. You could do either. Usually we split this function to be roughly separable. It doesn't have to be. Actually, I'd say our latest models don't do this. We have a much more complex setup. But in the first approximation, we can say they're roughly separable. We're neglecting here the eccentricity. It's not bad to assume all the eccentricities are 0. It's not great either in certain circumstances. So sometimes you may need to make it a 4-dimensional initial distribution. And there may be other parameters as well. If you're comparing to, for example, a whole galaxy, you'll have a variance of the metallicity as well, which makes it another parameter you need to put in for the single stars as well. So it gets very complicated very fast and very expensive very fast. But the first thing we do is we fix the metallicity in the other physics. That's fine. And the reason we do that is because this function, this delta bar, is a function of metallicity. So if we fix that so that we only need one set of stellar evolution models, run with one fixed metallicity. It's a lot easier and a lot faster and a lot simpler to do. You'll see this a lot. So you'll see papers where they have maybe 2 or 3 different metallicities instead of 1, but they don't run 100 different metallicities. Nobody does that because it's just too expensive. But then we can still vary the star formation rate relatively cheaply. And the reason for this is what we do is if we want to count stars in a phase of interest, now again I'm going to say the red giant branch here, we have stars born at different times. So I've got this axis here, which is the time, going from left to right. And at different times we have a different star formation rate. So the star formation rate here could vary. Okay. But the whole point is that the models that evolve from each of these points where stars form, that's these here, these are your different time steps from time 0, all the models are identical, which makes it very simple. So when they become a red giant, which is this red phase here in each of these tracks, that is the same for each of them, which makes it very simple. And the intersection with the now line, which is this line here, remember now is possibly many gigayears after the stars are formed, the intersection with that line and how many of them cross, so that's this one, and this one, that gives you the stellar number counts. Now what we can do is then rotate this diagram 90 degrees. And that's all I've done here. Exactly the same thing. I rotated it through 90 degrees. And what I then do is instead of running the time from top to bottom, I run it from left to right. And again, we count the number that intersect with this line, and that gives us the number counts, because that's exactly what we had on the previous plot. But all you have to do if you want to have a star formation rate that varies with time is apply in your stellar evolution model data a weighting function, which is a function of the look back time. And you will often see this in stellar population counts. Just have a quick think about this. It maybe takes a couple of minutes to understand exactly what I've done here. I've got a nice discussion in this paper from 2018. It explains a lot of what this is talking about. But the reason that we do this is that all we have to do if we want to vary the star formation rate is apply a weighting function to a single set of models. We don't have to rerun the models at each of these time steps up here. We just apply one function, this W function, as a function of look back time. This relies on you knowing when now is, but we know now is 13.7 gigayears after the beginning of the universe, or you know roughly when your galaxy was formed, maybe a gigayear after that, something like that. So have a think about this. You'll see that it's actually a very simple way to do things, but you can only do this if you fix the physics in the models. If physics is allowed to vary, if the metallicity varies with time, for example, you can't do this anymore. It's more complex. The other simplification that we often make when we do stellar populations is to fix the star formation rate. You might say to me, well, this is our star formation rate from the solar neighborhood. It's around the sun. You might say, well, that doesn't look very accurate. I mean, you can't fix that. It's wrong by a factor of 2. Yes, but the error bars on that are already 50%. So if the error bars are here, is it really that bad to say it's roughly constant? Probably not. And if you take this over a limited time period, let's find a different color that works better. If I just take this initial burst here, this is the burst that probably made the thick disk, for example. Then if we say that's roughly this constant here, that's not bad. It varies from 6 to 7 a little bit, but in the error bars it's probably okay. If you want to model young stars, well, the star formation rate fluctuates a bit, but it's roughly that. And if you want to take the average properly, you probably put it there, actually, because you've got it going up and down in spikes. You need to know the duration of the spikes. But to say it's constant over a short period of time, or even over the entire age of the galaxy, is not too bad in many cases. If you want to do accurate stuff, you need to get it right. But for just making your first population, it's a simple thing you can do. And then in the number ratios that you calculate, and if you calculate relative rates, that's the rate of, say, type 2 to type 1b supernovae, the S, the star formation rate, cancels out. That's why we do it, because the errors also cancel, well, to some extent cancel out. The uncertainties in the star formation rate go away, and it's all equivalent to saying S equals 1. I'm not saying that's real life, but it's a very good way of making a simple model quickly. So then your relative number rates will depend on this. We've seen this before. Your rates of things that you count. I want to quickly mention rates. Rates are things like supernovae. We don't count the duration of the supernova, we just count the number of them happening per year or something like that. Well, for that, you don't need this time step here because they don't have a duration. So all you do to calculate the rates is multiply that they're in the phase times the probabilities. And of course, that they're in the phase will be 1 in their case, when they happen, and 0 when they don't happen. So that's very easy to do for rates as well. But you've still got this big double sum over all stars and all time steps, but the S's cancel out. And the question is that good enough for what you're trying to do? And in many cases it is. And you know, consult colleagues, they'll give you an idea if it's good enough or not. So, but it's often done. Of course, the ultimate ideal model is to have a star formation rate that varies with time, but also models that vary with time. Here, for example, my phase of interest, I've changed how long it spends in the phase of interest. Maybe that's because the metallicity changes with time. Who knows? Star formation rate can change because the galaxy accretes less material, maybe more material, maybe there's a merger, something like that. Maybe you have interactions with other stars as well, maybe. But if you want to do this, this is full galactic chemical evolution, and it's a big challenge. It's still a big challenge today. So it's something certainly that many of you, I hope, will be interested in. So let's just recap these before we go into the next section. What we're trying to do in population synthesis is a combination of stellar models to make statistical predictions and compare to reality. Okay, it's kind of like being an accountant. Accountants are paid more, of course, but you get your soul. The accountant doesn't get their soul. You get to keep your soul, which is great. Okay. So let's talk a bit more about how we model stars in binary population modeling. Well, you know that our uniform mass grid was stupid. We shouldn't have done that. We can do better. That's one thing that we can do to improve things. But what about the models themselves? We showed that we can't directly use stellar evolution codes to do this because it's incredibly slow. You might be able to do it once, but you probably won't be able to do it twice. So if you make a mistake, you can't really do it again. So the question is whether they are fast enough, and usually they're not. So we have to come up with something a little more, a little smarter. Now, our parameter space, as we've seen, is multidimensional. It's one-dimensional for single stars at the minimum, three-dimensional for binaries, but it could also be more. Okay, so remember these n or n cubed parameters that are very important. What is the best way to sample this huge parameter space? Well, we could use a Monte Carlo approach. And here I'm going to show you a simulation, very simple simulation using random numbers. That's what Monte Carlo means. We choose randomly from the initial mass function. Okay, so we're choosing randomly masses from the initial mass function, and I'm going to use a salpeter mass function. And with the blue curve, I've plotted for n is 100 what we expect from the initial mass function. You see it drops off down here somewhere very quickly. So let me just switch to the animated version. So here you can see I'm pumping up the number. I'm starting with a few stars, and then I'm pumping up the number of stars until we get to 100. And you see we're starting to sample the parameter space pretty well. But if we just choose randomly selected stars, that makes no sense, because what we're doing is just sampling stars that are less than 1 solar mass. It's not a particularly smart way to do things. I mean, particularly because stars that are, say, 0.5 solar masses, which is the average mass of these stars, they don't really do anything. They're not very interesting in terms of interacting stars. They're very interesting in other ways. For example, if you look at massive magnetic fields in stars, then they're very interesting. But they're not so interesting in the binaries. Okay, so let's say we pump up the number of stars. Let's do 10 to the 4 to 10 to the 6 stars. Well, again, we're sampling this, and let's have a look there. You see that's nearly 500,000 stars. There's still some big gaps in the massive star population. There's a lot of noise up there. It's being sampled really badly. And that's one of the problems. Even when we get to 1 million stars, that's one of the problems with choosing Monte Carlo. And if your star is very interesting and it's around here, around this region, well, you've just underpredicted its rate by a factor of a few. So this is the kind of noise that you have from a Monte Carlo approach. It's one of the things to keep in mind if that's what you're using. But how may you go around about actually computing one of these populations? Well, what you do is you take a random number R and your distribution, which is the Salpeter distribution for the initial mass function. You normalize that to your total number very easily. And you could do this algebraically, but it's much better to do this numerically, and I wanted to show you quickly how to do this. What you do is you compute the cumulative distribution function, very easy to do. And then for this cumulative distribution, you choose your random number, let's say it's 0.7, which puts you up here. There we go. And it could be any random number, it could be from 0 to 1, that's any of them. And then you just draw a line across and then a line down, and that gives you a mass of 0.17. And you see the initial mass function, even here, has done a very good job of mostly, I mean, if you get up to 90%, that's down here, that's 0.3 solar masses is your 90th percentile, roughly, then that means most stars are very low mass, which is a peculiarity of the Salpeter IMF, I should say. The other IMFs are a bit flatter at that end. It's just an example. This shows you how you would generate from a random number. And remember, computers generate your random numbers between 0 and 1. That's what they do. So then you map that to the x-axis, and that gives you here 0.17 in this case. Or you can do this in an interpolation table. It's very quick. One of the issues with this, of course, is that if you do it on a log plot, which looks much nicer, I've plotted here 1 minus the cumulative distribution function. It's just easier. Then your 5 solar mass star is at this position, 1 minus 0.00001. You're very unlikely to choose stars there, and that's your problem with doing a Monte Carlo in quite this way. But the 5 solar mass stars may be the ones you're interested in, even though they're very rare. So you have to be very careful here. And you might need a lot of resolution in your table at this very, very small probability end. So the advantage of Monte Carlo is it's very simple. You apply more CPU, you have more stars. That's simple, it's very easy. It's like a real survey in some sense, because real survey, you just look at more stars, okay? And it models these natural fluctuations you have in stellar populations. The downsides are that your sampling is not guaranteed. We saw that in the high mass end. And so you've got this stochastic fluctuation, this random jitter like this, in your sample. Is that really what you want? Is that really what you observe? If you're looking at a galaxy, no. A galaxy has 100 billion stars, that's plenty, so you get a nice smooth distribution. It's very hard with this to increase the resolution where it's required. Now, if you're looking only at massive stars, you want the resolution there. Okay. And again, if you rerun it, you get a different result because you're choosing random numbers. You get different random numbers. So for small n, you can rerun it many times. It's a bit more expensive, and this is what's called bootstrapping in statistics. It gives you an idea of the errors, the numerical errors that are involved in your distributions that you compute. So you can do this in very practical ways, but you have to bear in mind the advantages and disadvantages. The other way to do this is to split your parameter space into a grid, or boxes, as we saw previously. This makes it much easier to do. I've done that here. I've split my mass range into lots of boxes, linearly in mass, which we'll come back to in a minute. And I've just said, well, the little bit of mass, the bin width, one of these bins, is just the maximum minus the minimum. It's about 100 divided by the number. It's very easy. And then you compute a model for each of these, and of course it's very easy to calculate, and you get the resolution you want, which is superb. Quick note on sampling: if you sample and compute the IMF, remember integrating the IMF, you should always get to 1. This is the normalization. This is because it's a probability density function. Then if you only have 100 stars on that on this plot, which I show this one here, your normalization sum is 0.25, which is definitely not 1. If you get enough stars, say you do 100,000 stars or 10,000 stars, this is starting to look much more like 1. But it's still not that close. Why is this? Well, because it's this power law which is very steep in the mass, is this function psi here. Remember, that's mass to the minus 2.3, which is very steep. So you're much better off using what's called a log grid, and then you can sum over all of your stars like this. And so you're taking then steps of delta log mass, natural log in this case, you could use log 10 if you prefer. But then if you only have 100 stars, you're already very close to 1 in your calculation. So what you will see in some of the examples we talk about in the next lecture is that we use log grids because of this, because it's a lot easier to get a much more realistic sampling of the initial mass function over a log spacing. This is something, if you've never done it, something to learn from today, if you learn nothing else. So there are advantages of a grid. You're guaranteed resolution, which I think is the big advantage of a grid. There's no statistical fluctuation per run, usually. You get the same results, reproducible, which actually in the modern day of computational simulations is very, very useful. You get to choose how to space the grid cells. Well, I've got an example of that next as well to show you how to do it. It's complicated in some senses, and there's disadvantages because you have to set up your multi-dimensional grid code. You can't just throw numbers at it. You have to set this up in advance. You need to calculate all these weighting functions, which is not trivial. And it's not like a real survey. It's more like a perfect survey. So a real survey has limitations in the number of stars it counts. Even Gaia doesn't see every single star in the galaxy. So there are limitations to this approach as well. I should say I usually use this approach because it's simple and good enough for most things we do. There is a hybrid approach which you can also use, which in each of these boxes, here, let's say we take a box, it takes a random point in the box, maybe there, maybe there, maybe there. And so you get a little bit of random noise, sort of jitter, as we call it, in the boxes. You can also do that. That smears out the results a little bit, but whether you need to do that or not, it's up to you. Oh, that's the wrong button, my fault. So here's a little case study. I was asked for some 3D isochrones by a colleague who works on clusters. And it seems simple. What they want is just some data. They want stellar properties at some time after a starburst, but they want 1 mega-year resolution, right? From 0 to 15 giga-years. 1 mega-year resolution, that's 15,000 isochrones. That's a lot. And then what they want in there is not just tracks for isochrones, but they actually want a 4D hypercube in luminosity, temperature, so this is your HRD, your Hertzsprung-Russell diagram, and they also want log G, because that's the observational Hertzsprung-Russell diagram. So they want a 4D hypercube. One of the sides has 15,000 points, the other sides are accurate to within 0.05 dex, which is what their observations were, which is tiny, tiny. Now that's a big, big data set. Now, what's the best strategy of sampling our stars to get this? Now you need to think first, because if you don't think, you're throwing your CPU at the problem. Remember the CO2, right? Remember your time. A PhD is 3 years. You could be spending the whole 3 years waiting for these to finish if you do this incorrectly. So we have to think a little bit about how do we sample the parameter space in a smart way. Now what we could do is we could say, well, we're going to sample the time resolution will be very poor at late times with a normal sampling grid. If we did a log grid, for example, a log mass grid, we get very poor sampling at late times. It's great at early times here. You see, this is a plot of log, well, it's on a log scale, right? And so the sampling time here, it's 0.0001. Very, very small. But up here, it's nearer to 10. That's your delta t. That's really poor as you get to later time. So your time scale, it's ridiculous at later time. It's ridiculously poor. You'd need a huge number of stars to get any kind of sampling in this that makes any sense at all. And the reason for this, of course, is that the mass of the star is linked to its age. And of course, that's when they do interesting things, is when they're old. So we can use this knowledge that we've got, the knowledge that you got from the single star classes, and we can say, well, okay, let's use this to sample things better. Well, stellar lifetimes scale is roughly some function of the mass. Okay, now you can get this very accurately from stellar evolution models, but let's just have a simple model here just to show what's going on. Let's say the time is m to the x, where x is around minus 2.5. It's up and down a bit. It doesn't matter for the purposes of this. And then we can say, okay, our time resolution, we take the derivative, we get the time step, essentially, the time resolution that we want. Take the derivative of this, and we get ax m to the x minus 1 delta m, where delta m is the spacing we're going to have. We just rearrange that, and it gives us our grid spacing, and then we can say, given a delta t, we then know what delta m is. So given delta t, we can say delta m is whatever it is. You choose this function f, this factor f, to be less than 1 because you want to oversample it a little bit. That's Shannon's sampling theorem. You don't know about sampling, something to learn about, but you want to oversample a little bit, otherwise you're going to end up with some noise. That's no good. So this factor f is something less than 1. But this now tells you what your delta m should be as a function of delta t, which you've got. I was given that, remember, by my colleague, 1 million years. That's easy. So that's fixed, that's given. F is just a number, and then the other things are from your lifetime function, which you know. So that's very simple. And then I end up with a sampling which gives me times like this. So I ended up with a lot more resolution at this end, and indeed, now it's absolutely perfect. And I only needed 16,000 stars in my population. So that was great. Everything worked perfectly. I saved an awful lot of time, which is really a good thing. Bit of thought gets you there. And indeed, this is showing you that at late times, we actually have a fixed delta t at late times. So it's very easy. So now we have the delta t we wanted, which is great. What about errors and uncertainties on these kind of distributions we plot? Well, okay, most counting errors are Poisson, roughly, right? So the errors go as 1 over square root of n. You could do a Monte Carlo simulation to show this if you want, or you can just believe me, it's pretty standard, it's very easy to show. There are other errors and uncertainties, such as not just counting errors, but systematic errors. For example, I've got a plot here which is from my PhD thesis, and it's carbon ejector from a population of stars as a function of the number of stars. Okay, and in the binaries, that's just on one side of the 3D parameter space, so it's n cubed. And you see the number itself fluctuates somewhat. It's kind of what you expect, right? You've got low numbers, you've got this error that you're going to in the counting. It's less of an issue for the binaries because you've got 100 cubed of them, so the numbers are just a lot higher to start with. But in both single and binary stars, you see that the numbers fluctuate and eventually converge to this number here or this number here, depending on how high you eventually go. But they do converge, which is the number that you want to represent. But if you'd started with a low resolution grid, maybe you'll have underestimated down here, and it would have given you a completely wrong number. So that's wrong by 20%. Maybe that's too much. Maybe that's okay for what you're doing. But until you actually make a plot like this, you don't know. The systematic errors also come in. These are where things depend on, in this case, I'm looking at barium yield as a function of carbon-13 in the star ring. Don't worry about it, this is an AGB style thing, but don't worry about that. But if I change this carbon-13 pocket mass, which I should say we don't know, or didn't at the time, then you get very different numbers. Okay, so the uncertainty range, because of a systematic, is also important. And these are really the troubling numbers in there. In stellar models, you have things like overshooting and stuff like that, and rotational mixing efficiency. These have to be calibrated to observe stars. It's the only way to pin down what these are. So that makes it very difficult. And what I normally do is split these into what are called fast and slow parameters. The fast parameters are those that you, given the stellar evolution, you only need to recalculate the fast parameter functions, such as the initial mass function, the initial distributions. Given the set of stellar models, you just need to change those, and that gives you these fast changes. It's a very simple computation to do, but if you need to change the physics inside the stellar model, that's what I call the slow parameter, you need to rerun everything. That's very expensive. So these fast parameters are cheap, the slow parameters are very expensive. Okay, and the slow parameters change how long you spend in each of your phases of evolution. The fast parameters change the initial distributions, so they change how many stars you have of each mass, for example. One other thing you will see in parameter space studies, particularly in binaries, is where your blobs of interesting stars disappear. I've got a plot here which shows these are the CH stars here in 2 parameters. I forget what they were, it doesn't matter. As I change the metallicity, this blob moves to the left. And you see, as I raise the metallicity up to near solar, which is 0.01, 0.02, what happens is the blob moves completely off the plot. And so the stars disappear. So many blobs you'll see of your interesting stars in the parameter space will disappear with certain parameters, which is a very, very good thing to know, because you can then compare that to observed stars, in this case with that metallicity, and say, are there any CH stars there? The answer is usually no. The red blobs, though, the red blobs don't change very much, and they're a pain, because if they don't change, find a different parameter to change. Now, the last thing we're going to look at are stellar evolution models. Now, stellar evolution models are slow and unreliable, I would say. Maser is great, but takes ages to run. Maser is great, but it crashes when you get to the AGB. That's not good. So what you need are things called synthetic models. These are fast, sometimes approximate codes that need the full stellar evolution codes as their input, but that's fine. I'll give you a quick example of this, and you will use these in the examples that we do in the next lecture. I've made here a Hertzsprung-Russell diagram of different mass stars on the zero-age main sequence. What we can do is we can construct functions which fit the zero-age main sequence. These are from this paper from 1989. You'll often see references to the Hurley papers, 2000, 2002. These are used throughout the industry. So these are simple formulae as a function of mass, very simple to calculate, very fast, and they're hugely faster than a normal code like Maser. Maybe 1 million times for the whole stellar evolution. Certainly they're a huge advantage. And the fitting formula gives you this. And you can see, why would you compute a zero-age main sequence if you can get it from the fitting formula? It's very easy. So if all you want are luminosities and temperatures, very easy. And you can split the evolution of the star into different phases, and you can calculate these fitting functions for all of these different phases. Indeed, that's what was done. If you look at the Hurley 2000, 2002 papers, those are the ones to look at. It's got collaborators as well, of course. And they split into many different stellar evolution phases. These are called the SSE or the BSE, single star evolution, binary star evolution phases. They're numbered. You'll see these used a lot. So they have main sequence, Hertzsprung gap, giant branches, core helium burning. You go through all the different phases of evolution. You also have these ones, helium stars, which are only in binaries, of course. They're stripped of their hydrogen, either through the binary or wind. So it's quite interesting. And there's also white dwarfs and neutron stars, things that eventually just sit there. So the stellar evolution phases you can define, and then what you can do is to compute how long is spent in each of these phases. For example, the main sequence lifetime is a relatively straightforward function. You can compute the luminosity and the radius as a function of this time as well. And this is how we do it when we run these models. This is a lot faster than computing full stellar evolution models. Now these alphas and betas, they're complicated functions, but the computer doesn't care, right? This is just code. Computer doesn't care, it just says that's easy. And it's very fast to compute. You can do the giant branches similarly. The way you do it with the giant branch is you say the luminosity is a power law of the core mass. That's been known since the 70s. And you also know that the luminosity is proportional to the rate of change of the core mass, because the core is where you're burning, so if you grow the core faster, you're burning faster, so you're making more luminosity. It's very simple. You can get these from detailed models, and then you can invert these functions to give you the rate of change of core mass as a function of time. So given an initial core mass at the end of the main sequence, the giant branch is easy. And then you can get things like this. So on the left, we have the detail models. On the right, we have the synthetic models. And, you know, they're pretty close. They're not that different. Most of the physics that's in the left plot is in the right plot. So it's relatively straightforward. And this one runs 10 to the 6 times faster, of course. Now, finally, because we have to finish here, I want to say that the latest developments in the field are to replace these functions with interpolation libraries. And interpolation libraries where you have a table, say, of maser data, so this is computed using maser, and then you interpolate on that. Very simple computation to do, not so simple to set up, because often the phase spaces that you're interpolating in are not simple cubes or hypercubes. They're actually got big gaps in them, and so you say, well, how do I interpolate, you know, hundreds of different parameters on each point? And that actually becomes quite difficult to do. We've been trying to do that a bit with machine learning as well, and there are things you can do to make it easier, but it's not trivial. We're developing something new called the MINT library. I had a postdoc the last couple of years doing that. We've made some success on the main sequence. That's actually very easy to do. After the main sequence, it becomes harder, but it's not impossible. It's just, it is a big struggle to get through and make it easy to interpolate. There's another code out there called the Poseidon code. There's another code being developed for SSE and BSE as well, which are the Fortran codes out there. The Poseidon code's a bit different, I should say. They are trying to interpolate binary models rather than single star models. Everything I've done so far is just use single star models. They're doing full binary models. I don't know why they're doing that. It would make sense just to compute all the binary models when you need them. But anyway, it's another way of doing things. Okay, so we've only run over a little bit, which is good. I'm sorry about that. So next time we'll look at a little bit more on observations. We'll compare observations to models, do a bit of statistics, a lot more on binary stars. I'll talk about them in quite some detail. And then I'll show you a few case studies. Okay, so this is where you go and you get my code and you run some stuff and you see how it looks. And the reason we're going to do that is because it's all about teaching you how to do stuff. It's much more fun if you're doing it than if I'm doing it. I've done it for 20 years. I don't need to do it anymore. You guys, we've now got the tools. They're all in Python. They're all very easy to install. So we'll do that next time. So thank you. Enjoy your coffee. I'm going to go make several pints of it now. So see you in a bit.